Look deep into nature, and then you will understand everything better. That's Albert Einstein. Welcome to Deep Dive. We're here to unpack complex topics and really get to the core insights, especially for you. Today, we are plunging into something truly remarkable, maybe even a bit mysterious for many. Slow motion earthquakes. Just imagine that for a second. An earthquake that doesn't happen in a sudden jolt, but actually unfolds almost silently over weeks, maybe even months.
Yeah, and this exploration today is really designed to give you a critical, kind of nuanced understanding of these events. If you're someone deeply interested in current affairs, perhaps navigating information for competitive exams like the UPSC, or even just for professional development, well, grasping these kinds of breakthroughs is incredibly important. We're pulling out the key insights from a pretty groundbreaking study. It's detailed in a publication by Ruud Bouguet, and it offers some really revolutionary perspectives on how our planet actually behaves. So our mission today is to decode what these slow motion events truly are, how scientists even manage to detect something so subtle, so deep, and really why they matter so much for understanding seismic activity and ultimately for our safety.
Okay, let's unpack this, because when most of us hear earthquake, you immediately picture, sudden, maybe violent shaking, that quick, intense jolt. So what exactly is a slow motion earthquake? How is it fundamentally different from what we normally think of?
Right, that's the perfect place to start because it really does challenge our usual picture. A slow motion earthquake is fundamentally different because it's a seismic event that unfolds over weeks, sometimes even months, instead of just seconds. Think of it less like a sudden snap and maybe more like a huge slow creep, almost like tectonic plates doing a very, very slow dance. So unlike that sudden rupture of a typical earthquake, these are incredibly subtle, really drawn-out movements of the Earth's crust. And this unique kind of prolonged behavior, it gives us crucial new insights into how stress builds up, how it shifts, and how it eventually gets released within the Earth's crust. It's subtle, yes, but it's letting scientists study the dynamics of a fault in a way that just wasn't possible before. It's like opening a window onto processes that are usually way too fast to observe properly.
That's really mind-boggling. I mean, if these movements are that subtle and so slow, how on earth do scientists even begin to detect them, especially, like you said, happening deep underwater, miles offshore? It sounds almost impossible, like trying to hear a pin drop in a storm. What kind of tech are we talking about?
You've really hit on one of the most amazing parts of this discovery. Detecting them was a phenomenal feat of engineering and strategy. It absolutely required putting these highly sophisticated borehole sensors in exactly the right places. Now, picture this. Drilling a deep, narrow shaft right into the ocean floor crust, maybe kilometers down. And then these specialized sensors are lowered into these holes. It lets them get inside the fault zone itself so they can directly measure tiny strains, minute shifts, things that instruments just on the surface or even just on the seafloor couldn't possibly pick up because of the water pressure and the distance.
Wow. Okay, so these borehole sensors are literally inside the crust, listening to the Earth's whispers.
Yeah,
That's incredible. And how sensitive are they? Can they really pick up movements that small?
precisely. They are astonishingly sensitive. We're not talking about just any sensors here. They can detect movements as small as a few millimeters. That's, less than the width of your fingernail. And that level of precision gives us data that, well, land-based systems like GPS networks, they just can't match. They're too far away and they can't see deep inside the crust like this. It's like trying to diagnose an internal problem just by looking at someone's skin versus getting an MRI scan.
So these incredibly specialized, super sensitive sensors, they were the real key to unlocking this whole secret of slow motion earthquakes. Sounds like a massive undertaking. Who was behind this? Was it one specific group?
It really was monumental, yeah. The core team was led by researchers from the University of Texas at Austin. Damian Saffer, he's the director of the University of Texas Institute for Geophysics. He specifically highlighted their crucial role. Their expertise in this kind of borehole tech in extreme environments was absolutely vital. And Josh Edgington, a doctoral student involved in the research, he helped describe the sort of mechanics of these events. He gave us that vivid ripple analogy we can talk about.
Right. So armed with these amazing sensors, what did they actually pick up? Were these just random events, or is this Nankai fault constantly doing this slow motion thing?
That's a great question. It's not like a constant hum. They actually captured very specific, significant seismic activity. The sensors first recorded a major slow motion event back in the fall of 2015. This was along what they call the tail of the Nankai Fault. And then there's another similar event they caught in 2020. And interestingly, both of these events traveled along a part of the fault that's already known for generating really destructive tsunamis. So that made the findings even more critical.
Okay, now this is where it gets really interesting for me. Analyzing these super subtle, slow movements, what did that tell the researchers about the Nankai Fault itself? What new things did they learn about how this huge geological feature actually works? Maybe things that go against what we thought.
This is where the real revelations are, absolutely. The analysis showed these seismic events weren't just simple block movements. They were more like waves of deformation traveling through the Earth's crust, a dynamic wave-like thing. Josh Edgson, he described it as akin to a ripple moving across the plate interface. So the plate interface, that's just the huge boundary where two tectonic plates meet and grind against each other, right? That's where most big quakes happen. But here, instead of a sudden break, it's this slow, wave-like movement spreading out, more like a ripple on water than a snap.
A ripple. But on the scale of tectonic plates, that's quite an image. You also mentioned an unzipping motion. What does that mean? What's actually unzipping?
Yeah, think about a zipper on your jacket, right? When you pull it, it doesn't just pop open all at once. It opens bit by bit progressively. So similarly, this unzipping motion describes how the fault doesn't slip all at once along its length. Instead, the two sides of the fault, they slip past each other sequentially in a kind of propagating wave. It's like the stress is being released segment by segment along the fault. The sensors track this very carefully. It started about 30 miles off the coast of Japan, then it moved steadily outwards, out to sea, and eventually kind of faded out at the edge of the continental margin. Just seeing that precise propagation pattern was a key discovery in itself. It shows how these stresses are gradually let go.
So not a sudden break, but more like a gradual peeling apart or releasing tension bit by bit, like a safety valve almost.
Yeah.
That's fascinating. And what does that imply about the Nankai Fault's role in the grand scheme of things?
Well, what's truly fascinating here, and maybe the most significant finding, is the implication. It suggests that this particular part of the Nankai Fault they studied acts more like a shock absorber. That's potentially a real game changer for understanding how faults work. Instead of just quietly building up huge amounts of pressure for a sudden catastrophic release, this segment seems to be actively easing that tectonic pressure gradually. So it means it's not necessarily contributing energy towards huge earthquakes and tsunamis in the same way other, maybe more locked parts of the fault might be. It challenges that simpler view of faults just storing up stress. It suggests some parts might actually be mitigating risk, which is, a crucial new piece of the puzzle for assessing seismic hazards globally.
That really is a fundamental shift in thinking, potentially impacting how we might predict major quakes. So if this part of the fault is acting like a shock absorber, what does this all mean for the bigger picture? Why is understanding these slow slip events so important, especially given the history of this specific fault?
Well, one of the most striking things is just their duration. As we mentioned, these events took several weeks just to travel 20 miles along the fault. Now compare that to a typical big earthquake rupture, which can travel hundreds of miles in, minutes or even seconds. This is just incredibly, incredibly slow. And that long duration gives us this unique chance to study the mechanics of stress release almost in slow motion, like watching a replay frame by frame. The research also gives really strong evidence for something scientists have suspected for a while, that these slow events tend to happen in areas with higher than normal geologic fluid pressures, so basically water trapped deep in the crust. It confirms that these fluids play a crucial role, almost like lubricating the fault, helping it to slip slowly instead of stipping and then breaking suddenly. Making that direct link between the fluid pressure and the slow slip is a big step forward in understanding why some parts of a fault behave this way.
And considering the Nankai Fault's history, did it have a massive earthquake relatively recently, geologically speaking? This new understanding must be really significant. But if it's acting like a shock absorber, does that mean the big one isn't coming? Or that it'll be smaller? That sounds a bit too optimistic.
That's a really important clarification, yeah. The last major earthquake along the Nankai Fault was back in 1946. It caused widespread devastation in Japan, showing its potential. And scientists are quite certain that another large seismic event is still expected along this fault system sometime in the future. That's pretty much a given over geological time. However, the fact that these slow slip events are happening regularly suggests the fault might be releasing some of its built-up energy gradually. This could, and I stress could potentially reduce the overall punch of a future large event, kind of like letting steam out of a pressure cooker slowly. But, and this is critical, we need a lot more research to confirm how much of an effect this really has. We definitely can't say it eliminates the risk, but it adds a really important layer to how we understand that risk. And if we zoom out to the bigger picture, these findings aren't just about Japan. By understanding how subduction zone faults like Nankai behave, and these are the types that cause the world's biggest earthquakes, researchers hope to get vital clues about the dynamics of huge quakes all around the Pacific Ring of Fire. It raises a key question for prediction, right? If some faults are releasing energy slowly, can we better pinpoint the truly dangerous locked sections that are just building up stress for a massive break? It shifts the focus a bit.
So this knowledge isn't just academically fascinating. It has huge real-world implications for safety, for preparedness, especially for places sitting near these major fault lines. It's about connecting the deep earth processes to the communities living above, isn't it?
Absolutely. Studying these slow motion earthquakes, it doesn't just deepen our basic science understanding, it has profound practical implications for mitigating risk. By figuring out where and how tectonic pressure is being released slowly, scientists can get a much better handle on the overall hazard posed by different parts of a fault line. And that knowledge is absolutely critical if you want to develop smarter strategies to lessen the risks from big earthquakes and the tsunamis they can trigger. It helps us prepare more effectively. Imagine having a clearer map of where energy is venting versus where it's dangerously building. Plus, just the ability to detect and monitor these slow slip events with this amazing sensor technology, it opens up whole new avenues for research. As scientists keep exploring fault behavior around the globe, maybe in places like Cascadia off the US West Coast, the potential for more accurate earthquake forecasting starts to look, well, increasingly feasible. It's a crucial step towards potentially saving lives and infrastructure down the line.
So today we've taken quite a deep dive into these silent, slow-motion tremors happening beneath our feet. We've uncovered how these gradual shifts on the Nankai Fault might be acting like the Earth's own shock absorbers. This research, highlighted in Rude Bouquet, is just a powerful reminder of how dynamic our planet is and how we're constantly learning more about it.
Exactly. And for you, the listener, whether you're trying to stay ahead of current affairs for something like the UPSC exams, or you're simply driven by curiosity about the natural world, understanding these kinds of nuances gives you a much richer perspective than you'd get from just a headline. It's about seeing those hidden processes shaping our world.
And thinking ahead, with these ongoing advancements in seismic monitoring, those incredible borehole sensors listening in, how might our understanding of earthquakes change even more in the coming years? What other secrets might the Earth reveal as our technology lets us listen even more closely to its subtle, slow movements? We really hope this deep dive has given you some valuable insights and maybe can spark some new questions. If you found this discussion useful, please do give this deep dive a like, subscribe to our channel for more explorations like this one, and definitely leave a comment below. Let us know if you have more questions or suggest other topics you'd like us to tackle next. Your engagement genuinely helps us bring more of these important discussions to you.